to talk about some of the work we've been doing on atmospheric contaminant deposition to the Athabasca Oil Sands region as part of the Joint Oil Sands Monitoring Program, or JOSM. So Colin already did a nice job of acknowledging some of the work that came before and really spurned the development of our program on atmospheric contaminant deposition. So this is not a new plot to most of you, I'm sure. But the point I just wanted to bring up is that Kelly et al., they used snowpack measurements at about 30 sites to show that contaminants such as PACs or PACs and some metals were elevated within the major development area. And similar findings were also shown by research out of the Wood Buffalo Environmental Association with lichen. So Colin also showed this diagram, just a very simplified schematic of some of the sources and transport mechanisms of some of the contaminants in the Athabasca Oil Sands region. And I say simplified because obviously all the different contaminants such as PACs, mercury, the different metals, they all behave differently in the environment due to their chemical properties. And I'm going to focus in today on the PACs and the mercury. So the primary tools or methods that we are using in our program are snowpack measurements, because if you sample the integrated snowpack profile at the end of the winter, then this sample actually represents a temporally integrated sample of contaminants deposited over the entire winter from the air to the land. The second method that we're using are the dated sediment cores, and Colin and Jennifer did a nice job of describing how these work. But in the absence of any pre-industrial monitoring in this region, they are really useful for looking at changes versus our background. And then, of course, we're forming strong linkages with people on the Air Quality Research Division side. They have a very nice passive air sampling network that's measuring PACs, precipitation sampling, and deposition modeling, as was shown earlier today. So we're forming trying to do some integration work with them as well. So one of the ways that we thought we could sort of advance the research on contaminant deposition in this area was to really vamp up the list of analytes that we're looking at. So polycyclic aromatic carbons, we're doing 52 analytes. We're also using some very new techniques, 2D GC time of flight mass spectrometry, to really identify novel PACs that we think could be used for source identification. So I'm going to talk a little bit about that. Multi-elements, 45 element suite, as Colin showed in the sediment cores. Mercury and methylmercury, a complete suite of water chemistry parameters. And then, of course, the paleo work we're also doing to look at trends in things like chlorophyll A, which is an indicator of changes in primary production in lakes, and various paleo-ecological indicators, including algal fossil remains, as well as invertebrate fossil remains. And these are useful for looking at the changes in the community assemblages of the algae and invertebrates that are in the lakes that we're coring. So I'm going to start with some of the snowpack work that we've been doing. So in 2011 and 2012, we started off with a sampling design that looked sort of like this. So in 2011, we just mimicked the 30 Kelly Schindler sites. And then in 2011, we really mimicked the Alberta Environment Snow Survey, where they kind of did a star design across the landscape. And one thing that we added in 2012 was some sampling in the Peace Athabasca Delta by Fort Chipewyan residents, because they were very interested in what was going on there. And then in 2014 and 2015, we really, I feel like we improved that sampling design by adding a gridded sampling design to give better spatial coverage on the landscape. And of course, this allows for a better fit for any interpolations via tools like krigging to your measured values. So I'm going to show some of the results. But before that, I want to talk a little bit about the work that we're doing in the Peace Athabasca Delta, because this is an important part of the project, and it's been a strong collaboration with the residents there since 2012. So the work there is important for a few different reasons. The first reason is because it is an important area that serves as background for us. And establishing background, as I'm going to talk about a little bit later, is very important, for example, for discussing what the actual footprint is. So we've been sampling 10 to 12 sites there, and also the residents are very interested in what's happening, obviously, in their home. And we have a lot of experience working in the Arctic, where we've engaged a lot of northern communities in our work there. So training the people there to do the sampling using clean techniques was fairly straightforward, and we've had a good program established for the last several years. All right, so here I'm just showing the net wintertime PAX deposition, and this is the total PAX. So one of our major goals was not to just describe spatial patterns in the deposition, which had already been done, but our goal was to interpolate measurements and create deposition maps for a region surrounding the development area. So we were able to do that with our 2012 design, which was the STAR design. And you can see the measured values are shown by the dots, and then the Kriged interpolations are shown with the shaded regions. And when we improved our sampling design to that gridded formation, we see a very good reproducibility in the deposition pattern. So this has been published in Manzano et al. Earlier this year. And I think coming up next, there's going to be another presentation by Dr. Kelly McKittrick, and he's going to show a slight reanalysis of these data. And we've been kind of going back and forth and sharing our different interpretations of the data, which has been really valuable. And one of the nice things that he has added is a very detailed map of the various industrial developments, which is something that we need to include in our analysis as well. What I would say is that when considering these analyses, we have to be careful about what we describe as background conditions. Because I think if you looked at the colored dots on the map, which are the measured values, it's clear that values in around the development area within around 50 kilometers are elevated above background, and background would be a blue measurement, which we don't even reach on this scaling here. So just a little bit about background and how we've determined background for this region. So we took 3 different approaches to try and get a feel, in the absence of any pre-industrial monitoring, what is background. So one of the tools we use is the measurements in the Peace Athabasca Delta, which are approximately, as you know, 200 kilometers from the major developments. We also compare those to loads in remote national parks in the Australian Alps, and the values we get from those 2 different measures compare quite nicely. And then we also plot the loads versus the distance from AR6, and we get this nice exponential decay function. And so if we use the load, or the y-intercept of that function, or where it flattens out, that value also agrees nicely with our Peace Athabasca Delta and other measurements. So when we use this value as background, we find that max loads are up to 1,000 times larger than background within 2 kilometers of the major developments. So just the point, again, that in the absence of any pre-industrial monitoring, a robust method for determining background is needed to quantify the extent of the industrial footprint, and the algal and invertebrate communities will be suited to the background conditions, and thus changes must be assessed against this background. So as I mentioned, one of the other goals of our project was to be able to estimate deposition to the landscape in this region. So here I'm showing comparison of 2 methods to estimate winter PAX deposition within 50 kilometers of AR6. So the first method is that exponential decay function, and that's the method that Kelly et al. Used in her first paper. And the second is from the kriging maps that I just showed you. And what you can see, oh, there we go, is that when we use the exponential decay function, the values are much lower. And this, of course, is because the exponential decay function assumes even distribution of contaminant deposition around the major developments, and it doesn't take into account things like wind direction. So we think that the kriging is a better tool for getting at landscape estimates of contaminant deposition. So now the next step that we're going to be doing is using our net springtime loads to pairing them with river water monitoring using GIS and hydrologic monitoring to actually determine the extent to which wintertime atmospheric deposition alters the contaminant concentrations and loads in the rivers, which are, of course, is of interest. So another way, of course, that we can get at background, another independent measure, is using these dated lake sediment cores. And as Colin said, we have about 25 from this region, located varying distances from the major developments. And so here I'm showing fluxes in both near-field lakes, which are, we've counted that as 10 to 50 kilometers from the major developments, and far-field lakes in blue, which are 75 to 185 kilometers from the major developments. And what you can see is there's a clear increase in unsubstituted packs, dibenzothiophenes, and alkylated packs since the onset of oil sands development in this region. And of course, we don't see the same trend in retine, which is a known indicator of things like forest fires, for example. And the largest increase in fluxes or deposition is seen in the dibenzothiophenes, and we see an increase of between 2 and 43 times above background in the near-field lakes in these dibenzothiophenes. I just wanted to mention to the add-on here the work that Carosi et al. Did, and so here is their max alkylated pack flux. So when you put it on our graph like this, it looks really tiny, but you have to consider the background, and their background is very, very low compared to our background. And so again, I would say that the increases, they see a doubling, are relative to the background in your particular area. So I want to just switch now to talk about some of the pack source identification work that has been done in our group using the 2D GC. So if you look at this, this panel here, this is kind of a routine packs analysis where we do 52 analytes. This is the chromatogram that you'll get from that. But when you use these 2D GC methods, you see that you get separation of hundreds of different chemicals. And this a method for doing this type of work has been published this year by Manzano et al. So when we did this work, we see that we've identified hundreds of novel chemicals, and the thiaarenes and azaarenes are a major component of the packs in the snow, sediments, and air. So what are these? Well, they are in lower concentrations than PAHs. Their sources include fossil fuels, soot, shale oils, and engine exhaust. And the key thing about them is that they include sulfur and nitrogen groups in them. So this is kind of what we think of when we think of PAHs, and these are these novel compounds that we are identifying now. So what we have done is we have identified about 230 different compounds, and we've grouped them into isomeric groups that have identical mass structure. So here are the 23 different groupings, and I'm showing the relative abundance of these different compounds. So you kind of get a fingerprint. So this is snow located at a site that was collected at WS1, around 25 kilometers from AR6. And this is the signature from delayed petcoke, and we got this sample from Jonathan Martin at the University of Alberta. And it is just one sample, but you can tell that the fingerprint of these novel compounds is pretty much identical. So moving on to some sediment cores. So this is one of our sediment cores. And this is the surface sediment. This is the pre-1985 sediment, and we can see that signature that's similar to petcoke. And then in the pre-1950 sediment, we no longer see that signature. And moving on, we also got one of Tom Harner's passive air samplers that was located about 30 kilometers from AR6. And again, we see that similar signature in the passive air sampler. So this shouldn't be surprising. Earlier this year, Zhang et al. Published a paper where they showed from their peat core work that they concluded that petcoke was a large contributor to the deposition that they were seeing from their peat cores. So I feel we think that we have a refined sort of schematic now for the sources and deposition of the packs in this region. We think that the petcoke is a major contributor to deposition within the region. So I just want to spend a couple last minutes talking about the methylmercury. And of course, we're concerned about mercury because the methylmercury is a neurotoxin, and it bioaccumulates and biomagnifies through food webs. And one point to make is that it takes a very small increase in the amount of inorganic mercury or methylmercury in an aquatic ecosystem to result in an increase in fish mercury concentrations or other biota in that ecosystem. So here's an identical map to what I've shown for the PACs. This is for 2014. And we see that max methylmercury and mercury loads are around 10 times background. And beyond 50 kilometers and in the Peace Athabasca Delta, both were near background levels. So some new work that we've been doing is trying to also look at the potential sources of methylmercury to snowpacks in this region. It's been long time hypothesized in the Arctic, for example, that methylmercury may be produced actually within snowpacks by bacteria there from the methylation of inorganic mercury. So we designed some experiments using mercury stable isotope tracers to quantify potential rates of mercury methylation in snowpack samples and snowmelt. And this is my master's student, Chelsea Willis, who's submitting this paper this week, actually. So what we see here are the rate constants for demethylation, or the conversion of methylmercury in snow to inorganic mercury, and these are the methylation rate constants. So what we see is that they are measurable, but they're very low. We also, since the petcoke seemed to be something that was important for the PACs, we wanted to look at this for the mercury as well. So we analyzed snowpack particles for methylmercury, and then we also measured the petcoke for methylmercury, and we had 3 different samples, also from John Martin. And what we see that the methylmercury in the petcoke is very low compared to what we see in the snowpack particles. So petcoke, not an important source of methylmercury to our snowpacks. And our results from the methylation experiments show that although snowpack methylation is possible, rates are too low to account for the quantity of methylmercury in the snowpack. So we're still looking for that source there. Looks like I'm running out of time. This morning, some of this work was already presented, so this is nothing new for today. But this is work that we've been doing with Ashu Dastur in the Air Quality Research Division. And what she is doing is using our snow measurements to validate their mercury deposition model. So here I've just kind of zoomed in for 2012 and 2014, but she's done it for 2013 and 15 as well. And this is, of course, the modeled measurements and our measured values with the dots. So do these values agree? Yes, they do. So this is the overall fit of the observed to the modeled measurements. And of course, I can't emphasize enough the importance of having a mercury deposition model for the region, because with this model that has been verified with actual measurements, deposition can be predicted under future projected emissions and climate scenarios, which is obviously an important tool to have. So some final thoughts. Maybe I'll just leave these up and I'll take any questions or get off the stage if it's time.
Ian Marine Associates. Just a question of how do you, I guess, solve the issue of the summer emissions versus the winter emissions and what that may mean in terms of what shows up in the snow?
Yeah, that's a good point. So obviously with the snowpack, we are measuring wintertime deposition only, which could be a completely different scenario than summertime. The sediment cores, you know, they are integrating, as Colin said, in each slice about a 10-year measurement, so we can compare and contrast with the sediment core data. And then there is precipitation measurements that are being carried out, not for mercury, unfortunately, but for metals, packs. One of the next steps is to coordinate with those precipitation measurements and look at seasonal variation, and of course working more with the air monitoring folks as well, because those the passive network that I was talking about, those go all year round and they're monthly samples. So lots of work to be done there for sure.